Let's take an example. Let's say we have the function f of x equals x cubed minus 3x squared minus 9x plus 4. And we want to find the intervals on which f is increasing or decreasing. All right, so we know what to do according to our rules up here. If the first derivative is positive, the function is increasing. If the first derivative is negative, the function is decreasing. So we need to set our derivatives with these particular inequalities and solve. All right, so we need to take f prime. Pretty simple few power rules here. We have 3x squared minus 6x minus 9. And what we want to do really is find where it's greater than 0, find where it's less than 0. It turns out that to solve a question like that, we really need to find out where it equals 0. Okay, so that's how we'll start. Even though our goal is for these inequalities, it turns out to solve these inequalities, we need to solve the corresponding equality. And that will lead us in the right direction. Okay? I need to solve this equation. Standard quadratic equation, I'll try to factor. So I'll take the 3 out. I'll be left with x squared minus 2x minus 3. And then factoring again, we'll have x minus 3, x plus 1. So we have a couple solutions. We have 3 and negative 1. So x equals 3, negative 1. Now, what have we actually found at the moment? We've actually found critical values of f, as discussed before, because we set the derivative equal to 0. Right, this is an important idea, but as it stands right now, the critical values, we're not really concerned about them as providing relative extrema at the moment, and they may or may not. Right now, we're just using them to help us solve the inequalities that we want to find answers to. So what you do now is you're just going to make a sign chart. So I have an x-axis here, and I take my critical values that I've found, 3 and negative 1, and I put them on here, scale irrelevant, so as long as the order is proper, 3 and negative 1. So these are the locations, again, where the derivative is 0. Right? So I want to talk about f prime here. Okay, so I know that f prime is 0 at these two locations, and only those two from the equation we solved. So therefore, everywhere else, right, this interval, and this interval, excluding these two values, I have 3 subintervals here, the derivative must be either positive or negative. And it turns out that the derivative will be all positive or all negative on any one of these intervals. Right? You can't change sign on any of these subintervals. Change sign from one to the other, but not on any particular one. So right now, this first interval up until negative 1 is either always positive for the first derivative or always negative for the first derivative. And we'll find out very easily. We'll just take a test case. Okay, we'll take a test case from the first interval. We'll test negative 2. That's certainly in the interval. I can't pick negative 1. That's not really in the interval, right? It's an endpoint, not included. So I'll test negative 2 back into the first derivative. And usually the best way to do that is to use the factored form. It's very easy to see what's going on there. And you don't have to do very many computations. So negative 2 I'm going to put into the first derivative factored form here. So negative 2 in here will yield negative 5. Negative 2 in here yields negative 1 for that factor. I'm not so concerned about the numbers. I'm just concerned about the signs, really, because this is a product. So I just need to figure out what the sign of the overall product is. So I would have a positive times a negative in this case. So that would be positive. So therefore, in this particular interval, the first derivative is always positive. Now I'll test a value from the middle interval. 0 is usually a good candidate if you have that as an opportunity. So I'll pick 0. Again, I'll put that into the factored form. If I put 0 in for x and 0 in for x, I'll get a negative factor and a positive factor. A negative times a positive is negative. So therefore, the first derivative must be negative on this interval. Now I'll take a test case from over here, maybe 4 or something. It doesn't really matter how far away you test from the endpoint here. I'm just going to pick the nearest thing so the numbers don't get too large. I'll test 4. This factor is now positive. This factor is now positive. And this factor was always positive, so therefore I have 3 positives multiplied together, yields a positive sign for the first derivative. Again, not caring so much about the actual quantity, just the sign. So you see how just using the critical values on this sign chart helps us to solve the inequalities. Right? So we see that here, right, let me just, and that's fine. First derivative was positive. First derivative was negative, and first derivative was positive. So therefore, that infers to us that this particular function, so f is increasing on 2 intervals. So negative infinity up until -1. We do not say it's increasing at -1 itself. We do not include the endpoints of these intervals. And 3 to infinity. F is decreasing on the middle interval of -1 to 3. And that is how to answer a question about the increasing and decreasing nature of a function. And you see all we did was solve inequalities just like these statements up here, and factoring was critical to dealing with situations like this.